Something you touched on earlier is sort of why it's important and why we should care about our software heritage. And I kind of want to get into a bit of that.
Yeah. So there are different reasons for different stakeholders, right? So a couple of examples that we usually use when we make presentation about software heritage is one, historical value, like the source code that put the first man on the moon, right? So the Apollo mission, that code is archived in software heritage. And that code is something that basically cannot be run any longer today. It's specific assembly code for the Apollo guidance computer. So it's completely pointless to even try to run it. But if you look at the comments in that code, it's the place where the team led by Margaret Hamilton invented software engineering as a discipline and invented a bunch of stuff that still exists today, like defensive programming. The fact that your program should be careful and should defend itself even against conditions that are not supposed to happen. Okay, so that piece of code is archived in our software heritage, and it's important for historical value, and we don't want to lose it. Okay, like other stuff that can be in a museum for a different branch of history to learn from. That's one example. Another example is in terms of innovation. So another typical piece of code that we show in our slide is the Quake source code, right? It has been open sourced a long time ago, authored originally by John Carmack. And in there, you find a very smart way of computing the inverse square root using only decimals, because that's the most efficient way to do that on consumer-grade hardware at the time. So I'm a scientist. So at the time, that kind of innovation could have been published in a computer graphics conference. Instead, it's in a piece of source code. So if we archive scientific papers because it's useful for the historical record and for the scientific record, then we should archive those pieces of source code. And these are just, if you want, like inspiring example, but you might also have a lot of practical reasons to do that, like digital obsolescence. Like maybe you've stored some images in a format that is not a standard, so it doesn't have a public specification available, but maybe someone implemented a reader for those images. So, okay, and maybe that reader is only stored in your own page or in your weird Git repository. So archiving it will enable someone down the road to actually read their images 20 years from now, rather than having them lost forever. Okay, and again, there are thousands of examples like that. But I guess the key lesson here is really that source code is important per se. It contains knowledge that should be preserved independently from even running that piece of source code.
I think not just necessarily preserving that old code so you can open an old file, but preserving it so if someone in the future wants to build a modern solution to that, they have an example of how it was once done. And maybe that way is not correct now and isn't going to run a modern system, but it gives you an example of how it was done so you can more easily understand a way to do it now.
Absolutely, that's absolutely the case. And source code, then someone expert can actually read it and make sense of it. And nowadays, we even have more and more useful tools to understand source code for us. For instance, LLMs themselves are actually really good at understanding code these days. So maybe once you have found a piece of old source code you care about, you can ask either an expert friend or some tooling to explain it to you and use it as a base to produce something else. Then there is also the entire aspect of scientific reproducibility. I don't know if that's something you wanted to touch upon. But
yeah, no, go ahead.
In open science, people have been talking about, so open science is this idea that essentially we should do science only using open artifacts that are available to everybody. Okay, and there are essentially three kinds of artifacts in science. One are the papers themselves, one are the data, and the third one is software. Okay, so in open science, a lot of people 10 years ago were still talking only primarily about open access to papers. Essentially, scientific papers should not be behind paywalls that only rich universities can afford. They should be available for the entire population. And they were talking a lot about open data. So data, same thing, right? They should not be by paywall. They should not be behind closed APIs. They should be available to everyone. The importance of open source software for open science was known. It's not like we invented it, but it was very much under discussed at the time. So our point is that if a scientific paper either produce some source code as a result or use some source code for running the experiment, which is the case in 99% of the experiment these days, by the way, and not only in hard science, right? And so that source code should be stored in a permanent place and referenced properly. And still to this day, we have way too many scientific papers that as a pointer to where the source code related to that paper use GitHub. Okay, and GitHub is the development platform. I mean, is a proprietary development platform, which is not my cup of tea. But okay, it's a successful collaborative development platform, but it's not an archive. So if you reference your source code in a paper with just a URL for the Git repository, that GitHub repository risks disappearing. Okay, and so it's really important that all the source code associated to scientific discoveries is stored in an archive like Software Heritage and referenced properly for posterity. And posterity can be my colleague, right? Can be my colleague that 2 years from now just want to retrieve my source code behind my experiment to actually build upon it, or to show that it was wrong. I mean, all sorts of good things come with public access to this kind of information.
Right, and if you have open data and open papers, but you don't have the software, you're sort of in a situation where you have to reinvent the software from the results of the paper and what the data says. You can't really you can't really just interpret the data without knowing how that data was actually being used.
Absolutely. So that is the use case of basically, standing on the shoulder of giants. So reusing some work done by others and build upon it. And then there is the reproducibility aspect. So I want to be able to rerun your experiments, maybe to verify it, because maybe you overlooked something. And so for that too, even if you don't want to build upon something, verification can only happen if you have, the entire dependency chain of the scientific experiment.
One of the things I was a little bit confused about when I first saw the archive was the what is it? The SWHID, the software hash identifier. So I guess maybe you could explain a bit of what that is and I guess why it exists.
So that is an identifier scheme that we have developed and that has been recently standardized as an ISO public standard.
That was done
it
last
means
year.
that is one of the few ISO standards that are publicly available. Okay, you don't need to pay for the specification. And so that standard essentially captures the way we identify all the objects we store in the archives. So I mentioned before this graph data model, and essentially, without entering into too technical details, the graph contains different kind of objects. Each one is a node in the graph. So one kind of node is a file, a specific version of the file. Another is a full directory of files. Another is a commit, which we call a revision. Another is a tag in Git that we call release, and so on and so forth, up to the full state of a Git repository. So we have one identifier that captures the entire state of a Git repository. And so essentially, the SWHIDs are a standardized way that we use to compute those identifiers. If people familiar with Git will notice that the basic scheme is actually compatible with what Git currently use, which are basically SHA-1-based identifiers. And these are used to identify all these kind of objects. So what we have done, essentially, we have standardized independently from Git how you compute these identifiers, provided some open source implementation so that everyone can do that, and actually release this to the public. And so the idea is that when you archive something in Software Heritage, you can see the identifier that something has received at different granularity, because maybe you care to reference a single file. Maybe you want to reference a full directory, maybe a commit, maybe the entire repository. And then later on, 10 years from now, you will retrieve the same thing from Software Heritage, and you will recompute yourself using an open source implementation, the identifier, and verify that they match. If they don't match, something has been modified, either in the archive or in the transfer. So it gives you some very strong integrity guarantees, which is something that you don't have with a lot of other identifiers out there. So we mentioned papers in science, DOI, digital object identifier, I use a lot to identify papers. They don't have these properties. So if you resolve today a DOI from a paper published 10 years ago, you can receive an entirely different paper and you would have no way to verify that. Okay. Because there are essentially men in the middle, usually they are a publisher and the operator of the DOI registry, that can make the DOI point to something else. that has some useful properties, okay, in the digital industry. I'm not completely saying it's a problem, but it's something that we wanted to avoid for digital first objects like source code artifacts.
Okay.
You can see the important implication for security, for example,
Sure.
here, right?
Yes. I didn't know that was a thing with papers. I was not aware of that at all. But I guess and this goes back to the whole open science thing you were saying, right? If you aren't able to reference the software that was used, how can you then, reproduce the results and do a further test with, like, you're not able to really do so if you aren't certain the software you're looking at is the same software.